All right, this new unit is all about polygons. We've already spent time in geometry looking at three-sided polygons called triangles, four-sided polygons called quadrilaterals, and now we're going to look at shapes that go beyond that. Again, a polygon is a closed path of three or more line segments where no two sides have a common endpoint and things like that. Okay, this would be an example of a pentagon. 1, 2, 3, 4, 5 sides. It then also does have 5 interior angles. These angles here are all the interior angles, right? The number of interior angles and the number of sides. Hopefully it makes sense that those are the same. We do have vocab words, just like in quadrilaterals where we have sides. We have interior angles. We have exterior angles. This orange line is the diagonal. We do have vertices, things like that. Polygons can be concave, like that, where they cave in on themselves. And then generally we're looking at convex. Again, we are going to spend an enormous amount of time looking at convex polygons. Okay, they each have special names. I think some of them you're probably familiar with already. So we know that a three-sided polygon is a triangle and then a quadrilateral. And then we have pentagon, hexagon, heptagon, octagon. Probably familiar with all of those. And then maybe not so much about nonagon, decagon. Don't worry about the 11. Dodecagon. And then don't even worry about that one. And then an n-gon. An n-gon is a way that we can talk about any bigger shape that may not have a specific name that we're going to know. Like if I wanted to talk about a 15-sided polygon, I could just call it a 15-gon. You then know that it for sure has 15 sides and 15 interior angles. Okay, I could talk about a 27-gon. It's got 27 sides. Okay, so they might use this in terms of talking about something bigger. But if they say like a 5-gon, they're just talking about a pentagon. They're talking about a polygon with 5 sides that also then has 5 interior angles. Okay, so again, these names, other than the 11 and the 20, you do need to know. So if I say octagon, you know it's 8. If I say heptagon, you know it's 7. And you should be able to spell them right as well. Again, we're going to look at polygons in this unit. We've used the word equilateral and equiangular when we talked about triangles. We could talk about the same thing in polygons, but really we're going to use the word regular. Regular is just going to mean it's equilateral and equiangular, and a regular polygon has all the same sides, and each of the interior and exterior angles are the same measure, which we'll talk about. Okay, let's talk about these two. Interior and exterior, I've mentioned those before, and we've done this before for triangles. But this is an example of an interior, right? There are 5 interior angles here, and then each one of the interior angles has a corresponding exterior angle. Hopefully you can see that the exterior and interior do make a linear pair, which means exterior plus interior equals 180 degrees in terms of their measure. This is not a regular pentagon. It's a pentagon, but it's not regular. It's not regular because the sides are not the same, thus the angle measurements are not the same, right? This looks a little bit more than 90, but this is significantly more than 90. And now it looks like maybe 100, and that looks like almost 130. It's a pentagon, but it's not a regular pentagon. A regular pentagon is one where all the sides and all the angles are going to be the same. Okay, below here is kind of interesting, but not really in the curriculum that we're going to discuss currently. And it's talking about how many diagonals there are for a polygon, and there is a relationship here. And maybe we'll investigate that later. But today, the lesson really is introducing you to the names of the polygons, and then we're going to investigate these interior and exterior angles. Okay, so this kind of just has it all out there for you. Okay, so look at this. This is a Greek letter called sigma. Sigma means the sum. It's a summing notation. You'll certainly do more of it in Algebra 2 and Calculus and beyond. But it means if you add up all the interior angles, this would be the sum. Okay? N is the number of sides, which also is the number of angles. So this is telling us that if we take n minus 2, and we get a number, and we multiply by 180, that's the sum of the interior angles in the polygon. So, for example, if n is equal to 3, we're talking about a triangle. Now, we already know that a triangle has 180 degrees inside. Okay, so we take 3, and you get 3 minus 2 is 1, 1 times 180 is 1, and then every time, of course, you increase the side, you're increasing the interior angle by 180, right? Any six-sided figure, right? Any sixagon, any hexagon has 720 total for the interior angle. And we could figure that out for any number of sides. Okay, just a really quick demonstration as to why this makes sense, right? This isn't like a full-blown proof, but like, why does this formula make sense? Well, we've proven before that we know that we take any triangle we want, and we know that there's 180 degrees in this guy, right? We know that that angle, and that angle is 180. Okay, what I'm claiming is that this formula makes sense that our triangle starts at 180, then every time we add another n, add another side to this, then we're going to get another 180 degrees. But that's pretty easy. Just add another side to this. Okay, now this huge figure here, 1, 2, 3, 4, is a quadrilateral. It's got an n of 4, which gives me another 180 degrees. Well, of course it does. All I really did is add another triangle, and that triangle we know has to have 180 degrees. If I added another side to it, that is now a 1, 2, 3, 4, 5. It's a 5-sided polygon called a pentagon. But what I added here was another 180 degree triangle. If you sum up all these interior angles, the interior angles of the 3 triangles is the same as the interior angles of the pentagon. And so we went from 180 to 360 to 540. And so that's really what this formula is telling us. Every time we add another side, we're going to add another triangle, which adds another 180 degrees. And so you can see that this goes up by 180 every time. If it's a regular polygon, well, then we can figure out what each one of the interior angles are. If it's not regular, well, then they all can be different. If you take any pentagon you want, I know that the total sum is 540. I don't know each of them are 180 unless you tell me it's regular. If it's regular, well, then I can take the top, this blue formula, and I can divide it by n, which is just taking the sum and dividing by n, which is the number of angles. And you're just equally dividing the total by the number of angles to give you each one of them. Again, this column right here, is only true if it's regular. This is true always. I can take any 6-sided convex polygon, and it's for sure going to have 720 total degrees. Now, if it's regular, then each of them are exactly 120. That makes sense? Let's draw that and kind of show you what I mean. If I attempt to draw, and this isn't perfect, but it's also probably not terrible. It's kind of freehand. That looks like a pretty close to a regular hexagon. A regular hexagon has 6 sides, and it also has 6 angles. We know from the formula that if I do n minus 2 times 180, so I do 4 times 180, I'm going to get 720 total degrees. If I take 720 and I equally divide them by n, the exact number, I get 120 for each. So I know that all of these, even if it's not regular, has to be 720. But if it's regular, then each one of these guys is 120 degrees. Okay? If I know the interior, then I also know the exterior, because I know that that's the interior, that's the exterior. They form a linear pair, and the exterior has to be 60. And so if you take any one of these and we extend those lines, right? Extend that line, extend that line, extend that line, extend the line, extend the line, and I look at all of these guys as exterior. What happens if I take this, I start here and I whip all the way around the circle? What do you think the sum of the exterior would have to be? Well, it went all the way around. Doesn't it seem like all the exteriors would have to be 360 degrees? And doesn't it seem right that actually that's true for any one of these shapes? If I start and I extend these lines and I do this exterior and I do this exterior and I do this exterior, if I go all the way around, doesn't it have to be 360? And that's what this next part is going to say, right? The top part talks about the sum of the interior, and then if it's regular, each interior. Down here, we're going to look at the exterior angle, and this column I think is just kind of funny because they're all clearly the same. The sum of all the exteriors, no matter how many sides, it has to be 360, right? The sum is 360 of exterior, because you go all the way around. They have to add up to 360. If it's regular, well then of course you can take the 360 and divide by how many to find each one. Again, go back to here. Look at the hexagon. All the way around is 360. If it's a regular hexagon, then it's 60, 60, 60, 60, 60, and 60. If it's a triangle, then we know that the interior angles are 60 because it's got a total of 60, 60, 60, 180. But the exterior actually have to be 120. Well, yeah, because if you only turn 3 times and you got to go all the way around to 360, each one of them would in fact have to be 120. And again, so this chart here, you can see as I increase the number of sides, I turn more, and so each turn ends up being less and less and less in terms of degree. If I only do 3 turns and the total has to be 360, well then each turn's got to be 120. For a square, any quadrilateral, it's 360, but if it's a square and it's regular, then each one of the turns has to be 90, 90, 90, 90 to get all the way around. And so today's worksheet is really investigating both of these things. It's looking at the interior angles, each interior angle if it's regular, exterior angles, and then each exterior if it actually is regular. Okay, so when you work through these problem set, you're going to use these facts. And again, I just want to remind you that it doesn't have to be a regular shape, right? Any pentagon I want, whether it's regular or not, this would not be a regular pentagon, right? This side and this side and this side, and the angles are not the same. But I still know that the sum is 5 minus 2 times 180. I know that there's still 540 total degrees, and I know that the total exterior has to be 360. Again, if I extend these lines, it doesn't matter. I have to turn, 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 turn. I do 5 turns that are not necessarily equal in size, 5 turns that have to get me 360. I know that this angle, this angle, this angle, this angle, and this angle have to be 540. So it's like if I tell you that, oh, that's 90, and this is 120, and this is 75, and oh, I don't know, I guess I'm just making up these numbers, and this is 115, and I say, what's X? Well, you know that all of the 5 added together have to be 540. They have to be. Now, if it's regular, well then you could have just taken the 540 and divided by 5 to get 108. But if it's not regular, it's still fine. It's still a pentagon. It still has to have 540. Okay? So you're going to use these formulas and investigate them, exterior, interior. You're certainly going to talk in general again about the actual names and shapes themselves. Again, what a polygon is, how many sides it has, the names of things. Hopefully this video gets you started, and we can start working on polygons.